About a dozen years ago, when we were starting to plan our first conference, I remember thinking that astronomy and cosmology and the whole subject of space exploration was going to be a fairly regular feature in these things. And I recall reading that our own galaxy, our own Milky Way, had something like 100 million stars in it. And I thought, geez, that's a big number, big number. And then a couple years later, I heard that it was maybe 200 million stars. And then a few years went by and someone said it was a billion stars, and we're still in our own galaxy, albeit it's one of the larger ones. It's apparently 120,000 light years across. And then the other day I heard our next speaker, Jayawardhana, say that there are a couple of 100 billion suns in just our own galaxy, and something like 80 billion galaxies in the universe that we know today. So from the origins of that universe, possibly one of many universes, some 13.7 billion years ago, all the way to the end of time, it's all too much and beyond exciting and fascinating. And so I'm thrilled to ask our own local U of T astronomer, rock star, Ray Jaya. Let me do that. Jayawardhana.
That's pretty darn good.
Okay, have you had to spell it as often as I've had to spell Zanana?
Yeah, just about.
All right.
Thank you.
This is Ray J. He's known as Ray J.
It's a pleasure to be here. And this afternoon, I'd like to tell you a little bit about the extraordinary age of discovery that we're living through. But first, just for a second, let's step back to a simpler time. We all knew the difference between stars and planets. Stars produce their own energy, planets reflected sunlight, and there were 9 of them. Remember that? Wasn't so long ago. And then astronomers started to discover these icy bodies in the outskirts of our own solar system beyond the orbit of Neptune, many of which turned out to be similar to Pluto, and some even had their own moons. One of them, now fittingly called Eris, after the Greek goddess of discord, appeared to be even bigger than Pluto. So this created a bit of a conundrum. Either we had to elevate Eris as the 10th planet, or we could open the door to dozens of others like it in the coming years. So school children would curse us for having to memorize 50 planet names. Or we could demote Pluto, which was the simpler choice that we made, to the great dismay of many. School children wrote us letters, calling us heartless or worse. Cartoonists had a field day. And there was at least one protest march that I know of in New Mexico. And 4 state houses in the United States passed unanimous resolutions declaring that Pluto shall remain a planet. What do these learned astronomers know? If you ever get a chance, look up the resolution from California, which is particularly amusing. It talks about how this change is causing psychological harm to some Californians who are starting to question their place in the universe and the constancy of universal truths. And they also called it an unfunded mandate because they had to change all these textbooks. So while Pluto and its brethren were getting all of this attention, I remember I was on 4 different television channels in Toronto that one evening when the vote on Pluto's fate happened. So this was not just in one place. Around the world, there was so much attention on this change. While this was going on, a much more fundamental revolution has been unfolding beyond the shores of our own solar system. After millennia of speculation and a century of failed attempts, in the 15 years since 1995, astronomers have discovered over 500 other worlds. So these are planets orbiting other stars that you see in the night sky. Suns like ours that we see as little dots in the night sky. They have their own retinues of planets. And that's a big change. From knowing about just the one solar system 20 years ago, now we know of hundreds of others. And this is no longer in the realm of speculation, this is in the realm of hard evidence. And many of these worlds are nothing like what we expected. They're so different in every way possible from the planets that we knew in our own local neighborhood. And it's been a long time coming because it's so challenging. And yet, once the first discoveries were made in the 1990s, the pace of discovery has been truly astounding. This chart just shows you how many planets were discovered in each of the years until the end of 2010. Just last year alone, astronomers discovered over 100 planets orbiting other stars. Think about that. That's incredible. Incredible pace of discovery. It's been a long time coming because planets are so faint compared to the stars that they circle. If you were to look at our own solar system from a nearby star system, what you will see is a bright sun, and then if you had the technology to detect the biggest of the planets in our solar system, Jupiter, it would be several 100 million times fainter than the sun, and the Earth would be even dimmer. So that's like trying to see faint embers next to a bright searchlight from miles away. Those embers are totally hidden in the bright glare of the searchlight. So this is the big challenge that astronomers have had to fight through to discover these worlds. And astronomers have had to be clever and devise a variety of other methods to find them. One of the first to succeed, and so far one of the most successful, is a method that involves measuring the wobble of a star because of an unseen planet tugging on it. Every time Jupiter goes around the sun itself moves around. Except it's so much more massive than even the biggest planet in our solar system, it doesn't do that. It sort of wobbles in place. If only you could measure that little wobble, the motion, you could infer the mass and the orbit of Jupiter and its various properties. And this is a technique that Canadians like Gordon Walker pioneered back in the 70s. It really was incredible foresight to think of a day when you might apply techniques like this to discover other worlds orbiting other suns. So today, astronomers have surveys of thousands of nearby stars, taking their spectra, seeing these little lines in their spectra that move back and forth towards the red, towards the blue, and that little shift, the subtle shifts, tell us the motion of the stars, which in turn tell us what planets are circling them. A second method that's worked out has depended on something we knew about in our own solar system for hundreds of years. And that is, when we look at our sun, every once in a while we see the two inner planets, Venus and Mercury, passing in front of the sun, like little black dots. And in fact, the next one is going to happen in June next year, the next passage of Mercury in front of the sun. We call it a transit. In fact, in the old days, this was one of the ways that we measured distances in our own solar system. This was the reason, in fact, that Captain Cook was sent to Tahiti in 1769. That whole expedition was about observing a transit of Mercury, because that was the place to see it. And now we can use the same kind of idea, the same technique to look for planets orbiting other suns, except we see other suns as little dots in the night sky, the stars. We don't see them as big balls of light in the sky like the sun. So what we can do is not to see the little dots of passing in front of the stars, but we can see the stars dimming by just a few percent or 1% or less every time a planet passes in front and blocks a little bit of that starlight. So let's imagine a planet passes in front, blocks a bit of starlight, the star dims for a few hours, and the planet goes away, the star comes back to its normal brightness. Of course, this only happens if the planet happens to be orbiting in this plane, right, where you're looking at it edge on. If it was doing this, you'll never see it passing in front of the star, because it's in a completely different plane. It's not edge on. So this way, you only catch some fraction of the planets, and to succeed, astronomers usually have to monitor thousands of stars in the night sky to find a few. But once you succeed, you get a size of the planet from the size of that dip. A planet about the size of Jupiter causes a star to dim by about 1%. The planet about the size of the Earth, it causes a dip only about 1 part in 10,000. So that's pretty hard to do from the ground. But for the big planets, even small telescopes that amateur astronomers have in their backyard are good enough to make this kind of precise measurement. So in my book, I talk about, for example, work done by amateur astronomers around the world. There's a third technique called microlensing, where a housewife outside Auckland, New Zealand, contributed to discovering the second microlensing planet ever. So there's a variety of people from around the world involved in this unfolding drama. And then all this time I was trying to tell you how hard it is to take pictures of planets. Yet a couple of years ago, we took this picture of a little dot next to a bright young star, and we said that's a picture of an alien planet. How did we do that? There were a few tricks we used. We looked at young stars because young planets are much brighter than old ones. Because young planets are still forming, they're still contracting, they're still shrinking in size, they produce their own heat. So they're only about 10,000 times fainter than their star, rather than several hundred million. So that gives us a big gain. The second thing that helped is this is a big young planet, a hot one, and it's pretty far from its star. It's about 11 times further away from its star than Neptune is from the sun. So it's pretty far out, it's easier to separate their light. The third thing that helped was technology. In particular, technology called adaptive optics, which allows us to basically take the twinkle out of the stars. Sounds kind of sad, but it allows us to take very sharp pictures of stars to see faint little dots next to them. And that's how we were able to take a picture, a direct picture of a planet orbiting another sun. And since then, a few other groups have done the same. By the way, we got a lot of media, including this tabloid in Sweden. That's when you know you made it in life. Everybody can make it to the New York Times, but how many scientists make it in the tabloid world, right? Since then, a number of other discoveries have been made of direct images of planets orbiting other suns, including this spectacular one done by another Canadian team led by Christian Marois at the Hertzberg Institute in Victoria, which is actually a family portrait of a planetary system. What you're looking at are 1, 2, 3, 4 big planets orbiting that star. The star itself has been subtracted out to be able to see the faint dots next to it. You can actually see over a couple of years these 4 planets orbiting the star. Not a full orbit yet, but you can see parts of their orbits. Imagine that. You take a picture today, come back 2 years later, the planets have moved around just a bit. Incredible. A family portrait of another planetary system. Of course, now the race is on to look for planets like the Earth. This is the new frontier, and it is a frontier in which Kepler, a NASA space probe, a space telescope, is playing a big role. So this 1-meter class space telescope was launched just in 2009, March of 2009, from Cape Canaveral, and it's orbiting the sun, and it's staring at a little patch of the sky that's about the size of my palm at arm's length. That is the size of the patch of the sky that Kepler is staring at. And it's staring at it for at least 3.5 years, we hope. And the reason it's doing that is there are millions of stars in that little patch of the sky. About 150,000 of them are bright enough that Kepler can make precise enough measurements to detect a planet roughly the size of the Earth. So now, for the first time in history, we have the technological capability to look for Earth twins orbiting other suns. So it's an incredible moment that we're really sitting right here while Kepler is doing its thing, monitoring all these stars. And just in the first year of its data that astronomers released in February, they found over 1,200 planet candidates. Think about that. I told you 500-odd planets in 15 years. Kepler comes along, the floodgates open, 1,200 planet candidates in one single year. It's an incredible pace of discovery that continues to accelerate. And among these worlds that Kepler has indicated exist is an incredible planetary system of 6 planets seen in transit. I told you about planets passing in front of the star. Here's a case, 6 different planets are seen passing in front of the same star. It's a 6-planet system. What's even more remarkable is that 5 of these 6 planets, their orbits fit inside the orbit of Mercury in our solar system. How incredibly rich is that, right? And these planets are big ones. They're roughly the size of Neptune. 5 of them fit inside the innermost planet of our solar system. Not only that, because they're so close to each other, we can actually measure their gravitational tug on each other as well. That means we're sort of seeing a beautiful dance of these 5 worlds choreographed by gravity. and we're watching it in real time. It's an incredibly beautiful, unexpected, surprising discovery. And this is just one example of the myriad planetary systems that are being revealed. Now, one problem with Kepler, of course, is most of the planets it's going to discover are around stars that are too faint that we're not going to be able to do a lot of follow-up. And that's where ground-based telescopes come in, like the M-Earth project based in Arizona, which is looking for some of the nearest stars, small nearby stars, looking to see planets that are only a little bit bigger than the Earth, catch them in transit, because those would be much better targets to detect their atmospheres, to characterize them. And they have already one object, and we, my graduate student Bryce Kroll, and our collaborators have used the Canada-France-Hawaii telescope, which is on Mauna Kea in Hawaii, pretty modest-sized telescope by today's standards, to actually measure its atmosphere. Now we talk about measuring the atmosphere of a pretty small planet, only a few times bigger than the Earth, as it passes in front of the star, from a ground-based existing modest-sized telescope. So this is the kind of technique that we're developing that we someday hope will allow us to detect interesting molecules like oxygen, ozone, methane, water, all of these molecules that we today call biosignatures, things that we associate with the presence of life as we know it. And that's, of course, the grand question that we all want to know the answer to, not just as astronomers or scientists, but as human beings. Are we alone? What is the evidence? Can we, as Moses said, 200 billion suns in our galaxy, 80 billion galaxies, the odds, of course, say there's got to be life elsewhere. But that's one thing to speculate, and quite another thing to actually have evidence. And that's what we're going after. Now, the big challenge is, even if you detect these molecules, it's circumstantial evidence, because you're not really, you're detecting all these elements that exist in nature. They could or could not be related to life. But let's say we find multiple biosignatures. We still wouldn't know whether they indicate slime or civilization. And would that make a difference to you? I don't know, does it? So that's a question I tackled in this opinion piece in the New York Times in March. The question is, if we can't tell, or if we think it might be slime, would it just be a one-week news story and we move on to other things, here by Earth concerns? Or if we were to detect a radio signal or some other technological signal that is definitively of non-natural origin, then maybe that will be a much bigger deal. Because even if you can't decode it, even if you can't tell what the message is telling us, just the fact that it's an artificial signal is telling us somebody is at the other end that has the technology to send it. And maybe that will be a much more dramatic moment. In many ways, regardless, I think we're already in a moment in time that is in some ways similar to when Galileo first turned his telescope at the heavens 400 years ago. In particular, when he turned his telescope at Jupiter, and he saw the 4 big moons around Jupiter that are circling it. So for the first time, Copernicus said, the sun is at the center of the universe, not the Earth. Galileo came along, here's the evidence. Not everything in the universe revolves around us. Look at these 4 moons. They're orbiting Jupiter, not the Earth. In some sense, that was pretty dramatic, looking back, to have direct evidence of how we stack up, where our place is in the universe. And I think in some sense, we're at a stage where sort of completion of the Copernican revolution, we're trying to find out our true place in the universe, our true measure in the cosmic sense. And that is a story that is unfolding right here, right now. And I hope you'll be excited to learn about what's going on here in Toronto, in Canada, around the world, with a wide variety of people involved in pushing the frontiers. And it's been a very exciting time and a very exciting experience for me to be involved in a little bit of that. Thank you very much.
Strange New Worlds, The Search for Alien Planets and Life Beyond Our Solar System. I recommend you get it. Ray, I want to ask you a question. Some of the most prominent cultural heroes of our day are people who work in technology. Steve Jobs and Mark Zuckerberg, and before him, Bill Gates, and Carl Sagan was a very prominent personality. And yet, you say that you don't get the feeling that science and technology are part of our cultural identity. What do you mean?
You're putting me on the spot. So this is a bit of a comment I made. I grew up in Sri Lanka, got inspired hearing about the moon landing as a 4-year-old, came to the United States, studied there, worked there, and I moved to Canada. And I felt that Canadians are very proud of their art, their literature, their music. It's very much, you can go to the pub and people will talk about it. You'll hear it all the time. You don't hear, at least I didn't hear, people talking about science and technology as being part of the cultural identity of this country. And in the US, you can be critical in some ways about various things. You can point to creationist arguments for not against teaching evolution. But on the other hand, at least in the sense that most Americans have a sense that technology had something to do with their dominance in the world, even if it's in the military sense. And I think whatever sense it is, there's that sense of the moon landing, the military technology, and then now Silicon Valley are really sort of part of their self-identity. And I think that's sort of what I was commenting on, and I'm willing to be corrected.
Do you think the
just an observation.
Do you think the Canadian educational system is deficient in these areas?
No, not at all. I think it's more sort of a cultural thing, and it's sort of a more how do we see ourselves? Do we see ourselves as playing a role in these arenas at on a world-class level? And I think that's more the question.
We've got an arm out there, don't we?
We do. Well, it won't be for very long. One more shuttle mission left.
One more shuttle.
Yes.
Well, thank you so much for your appearance.
Wonderful to be here.
It's great. It's a great picture.
All right. Thanks.
Ray J.